Hello everyone, my name is Varan Voskarchan. I'm a PhD student at the University of Vigo, and my research topic is about flexible and highly scalable LiDAR for an FMCW LiDAR PIC based on grating couplers. The main objective of my research topic is to investigate conventional photonic integrated circuits, optical phased array systems, and to make a new concept LiDAR system based on a tilted grating couplers, to do the proof of concept using FFT simulation, then to fabricate the device, realize the lens system, and to do the device under test experiments. First system that was investigated is a HFire optical phased array system, and in the HFire optical phased array system, the light is emitted into the free space by the interference from the edge emitters and can be individually modulated by applying phase shifters onto the waveguides. One of the main parameters of this HFire system is the field of view, and also for optical phased array systems, which shows the free ambiguity steering range. And another parameter is the full width half maximum of the beam, which shows the minimum size of the detectable object. The simulations have been done for this HFire system, and it is shown that the 0.1 degree full width half maximum is achieved when using 1,500 elements spaced at a distance of 0.77 micrometers. And in this graph, you can see that the relationship between the number of waveguides and the full width half maximum. Also, the far field intensity was simulated, and the random phase perturbations were also taken into the account, because in the real life scenarios, we will not have the uniform far field, but rather the perturbations in the systems. Another system that was investigated is the grating coupler phased array, and the schematic structure of the grating coupler is given here. So it was simulated for this structure, and the angle emission in the grating coupler is given by the Bragg condition. By varying the period of the grating teeth in the grating coupler, we can have the radiation in the desired angle. And these are just the far field from the several parameters of the grating coupler. This is just a 3D far field pattern from the grating coupler phased array with the grating teeth number of 50. And we can see when we have the grating teeth number 150, the far field intensity shrinks. The width of the far field intensity pattern is smaller. So just here, we showed what parameters influence the far field. Next, the steering and random phase perturbations was also simulated for the grating coupler optical phased array. Here, the ideal case is the red one, and the black case is the ideal case is the red one, and the black case is the random phase, and also the steering capabilities were simulated for the number of the grating coupler elements, 1,000. And in this research, we are proposing a new type of system based on the tilted grating coupler, which you can see here. So they are based on the same structure as the conventional grating coupler, but instead of having the grating teeth straight, we give it a small slant angle, and so we can emit the light in different angles. So the transceiver and receiver grating couplers will be spaced next to each other, and everything will be collimated by the cylindrical lens. And then when the light comes, it focuses on every receiver tilted grating coupler, and then is detected by the photodetectors. Here are just some numerical results from this system. Here you can see the radiation relation from the tilted angle, and we can see that we can have a radiation direction around 60 degree. And here is the far field pattern from the 33 elements, and the distance between the individual transceiver grating couplers are 20 micrometers. And here is the simulated optical powers coupled of the grating couplers based on the angle of the slant. Also, the diffraction angle was also simulated. So when changing the wavelength, because in the system we are going to use a tunable laser, we can see that by the changing the wavelength, we can also have a steering in the azimuthal direction. For the lens design, we are going to use a cylindrical lens, but just using one cylindrical lens will introduce aberrations into the system. And we want the light to uniformly focused on the chip plane. And for that, we are going to use a camera lens system, which can focus the light from 34 degrees to minus 34 degrees to plus 44 degrees. And also it can collimate the beam that is coming out of the chip plane. The width of the grating couplers were calculated by taking the point spread function of the individual beam. So we can see that the farther we go in the to the angle 34 degree, the wider the big beam becomes. So we will use so the width of the grating couplers will change based on the field angle that is coming from the space. So in conclusion, we have proposed and evaluated the concept for FMC LiDAR PIC, and we show the feasibility of the concept and that it's possible to have a field of view of 100 by 12 degrees. And our architecture offers many advantages over the existing LiDAR architectures, such as it's highly scalable, flexible, and it doesn't require to use phase modulators, which can complicate the system. Yeah, thanks for the attention.